So this gives a incentive to uh, manipulate the outcome of an election. So so can one manipulate the outcome? So when we say manipulate the outcome, we mean that who wins the election. So can one control who wins the election by redrawing the district line? So we are familiar with election system, and in the election generally there are district and or polls, and voters go to a poll, and there are constituencies from where a candidate wins, and finally based on which party from which party many more of the candidates have won, based on that the final outcome of the election is decided, right? So there in most of the places the election have this hierarchical structure. And so now this the question that we ask here is, can we change this, how the districts are structured, who votes in which voter votes in which district, and based on this can we change the outcome of the election? And this question is formally known as gerrymandering. And why would one want to do, just to want to win a more district? Maybe they want to control the state budget for that district, or they want to more district in future. And these are practical motivations. So as I will show you in the next example, so this is an example of US North Carolina state election. And this there as the poll suggested, the initial poll suggested that there are 50%, almost 50%, voters are divided almost 50% between Republican and Democrats. And so there I will just call them blue and red voters. So there, as you see, that there is almost 50% blue voters, and there are 13 seats here. So you would assume that if the voters distribution towards the parties are like this, then there will be among the 13 seats, 6 seats probably will be owned by the blue candidate, and 6 seats will be owned by the red candidate. But this is not what happened. This is what happened. Only 3 seats were won by blue candidate, and remaining seats were owned by the red candidate. And this is very abnormal, right? Because you have almost 50% of the voters are voting for the blue candidate. So how did this happen? And this is what is the magic of gerrymandering. So this is what the Carolina state voters look like. So there are, this is how the voters were divided into districts. So each of these are one district. So as you can see here that there are 3 districts where the blue candidates own, and all the blue voters who are voting for the blue candidates are very densely packed inside these 3 districts. And the remaining seats, the red candidates are the voters who are voting for the red candidates are distributed. And this is how the red candidate own a lot of seats into the party. So to formally this problem has recently gained a lot of election, and this has become a very common phenomenon in US elections. So the the problem that we will be looking at is where the voters are vertices of a graph. So and so the previous North Carolina election example that you saw, so what we did there, what happened there, that there was a set of voters, and we wanted to partition it into some number of districts. And the red candidate basically partitioned it, the district, or drew the district line in such a fashion, then they own a large number of districts, right? So now if the voters are on a graph, which is a natural to look at, because the districts are generally drawn on the map, so you can assume that the voters have some connectivity between them. So the voters are on the graph, then you cannot partition the voters arbitrarily. You have to so what you want is that a district must be connected. So we want to partition the vertices vertices of the graph such that each partition is connected, and this is a connected partition of, or a connected subset of the vertices, is what we will be calling district for our problem today. And each voter approves one candidate, that is, each voter votes for one candidate, as we saw in that example. And the maximum number of like the majority, whoever has whichever candidate has the majority in each of the district, they will win. So so this problem on graph was formally defined in 2018, amas by Cohen, Jemak et al. And so the problem formally, you have this n voters and you have m candidates. So the example that we saw there, we had only red and blue candidates. So formally you can have m candidates, and each candidate gives vote to one, each voter gives vote to one candidate, that is each vertex, sorry, this arrow should be in the other direction. Each vertex gives votes to one, approves one candidate, and each vertex also have a weight. As I said, that sometimes the vertices are not really representing just a single voter, but they're representing election poll. So so the number of voters voting into that poll could be represented by this weight, or there could be other situations. So each vertex has a weight, and a candidate, if this vertex votes for a candidate, the candidate gains those many votes. Like so this weight is any integer. And so now I have a preferred candidate, and we want and we are given an integer k. So what we will want is that we want to partition uh, the vertices of the graph into k partitions. That is, we want k districts, and finally we want that our preferred candidate win in majority of the district. That is, win in not majority, sorry, win in more district than any other candidate. So what I will formally define what we mean by winning a district. So a candidate Q wins a district V prime. Now that V prime is a subset of the vertex set. So it wins wins the vertex district V prime if the weights it's gaining from the V prime is the set of vertices in V prime is maximum, right? So so this is what this expression means, right? That V approves Q prime, and the weight of V is what Q prime gets if V approves Q prime, and the total weight it gets. So this is what formally means to say that a candidate wins into a district. And the question we ask is, as I said, that we want to divide the vertex set into k disjoint parts, and each part must be connected. And we finally want that our preferred candidate P wins in more district than any other candidate, and P must win uniquely in more district than any other candidate. So so this problem so we so we give a generalization of this model. So a very natural generalization would be that as I said, that each vertex is defining it might correspond to a poll, where so in a poll all the voters, it's possible that all the voters in a poll does not vote just for one candidate, but multiple candidate gains votes from there. So what our model looks like is that instead of having an approval function and a weight function, we have a weight function where where the voter gives 0 or weights to those candidates whom he does not approve, and some positive weights to the candidates whom he approves. And this this now with this new definition of weight function, uh, what does it mean to say that candidate Q wins in a district? If now the weight function, exactly the same thing, just with since the weight function is now changed, we have changed this expression, that it's again the total number of sum of total weights the candidate gains from the district, that is from the vertices in the district. So the question remains same, and this is a general model, because if so you can get an instance of the previous model, which will be referring as GM, and this model as weighted gerrymandering as WGM. So the previous model, if you so to get the previous model, if you set this value to be 1 just for one candidate, non-zero just for one candidate, that is the candidate that you approve, and 0 for everybody else, this gives you the previous model that we were looking at, right? So so now I'll look at some of the existing results, and what are the results that we prove here. So this problem was studied by et al. In 2019, and they show that this problem is NP complete even if K is 2, that is, there you want only 2 district, and the number of candidates is also 2, and when the given graph is a complete bipartite graph or a complete graph. So what does this mean? That since this is actually para NP hard parameterized by K and M, so you cannot have an FPT or even XP parameterized by K plus M on general graphs, even or even on planar graphs, because this is a planar graph, right? K2N, and you cannot even have so this graph, if you delete just one vertex, this becomes a forest, right? So again, that means even with vertices which has FES size 1, for them also you cannot have an FPT parameterized by K plus M. So we have to, if we are not, and in general we want to parameterize yeah, so if we have to get an efficient algorithm, some FPT algorithm, we need to look at some graph classes, some restricted classes of graphs. So that means we have to, this second results says that it's better to look at forest or some subset of acyclic graphs. So first we proved that this problem is NP complete on paths, and I mentioned that in this reduction we have non-unit weights, but recently there is another paper in arXiv which proves that the same result with unit weights. Then I'll move towards the positive results that we prove. So in each district, as I said, we defined that what does it mean to say a candidate wins in a district, right? So multiple candidate can gain maximum weight in a district. So to avoid that multiple winner in a district, it is we can define a tie-breaking rule, and this could be defined based on like some popularity, some lexicographic ordering, or previous records, or anything. So some based on some rule, you define a tie-breaking rule, and so that can give you unique winner for each of the districts. And if we assume this, then based on then we prove that for paths for weighted gerrymandering problem, we can get a deterministic algorithm which runs in time 2.619 power k, and randomized algorithm which runs in 2 power k. And for general graphs, we give algorithm which runs in power to time 2 power n. So I'll mainly describe the algorithms on paths, and if time permits, I will go into the algorithm for general graphs. Okay, so this, let's look at what are we trying to do. So we have this instance of weighted gerrymandering. That means we have this voters, and there. Yes, is there a question? No, I suppose. Okay,
Yes,
so
I have a question.
yes,
Sanjukta, I have a question.
yeah.
What do you mean by gerrymandering on graphs, basically? Actually, I have missed from first 5 minutes. What is the meaning? Yes, what is the meaning of this gerrymandering on graphs?
Okay, I'll try to explain it on the slide itself. Okay, stay.
Okay,
So
thank you so much. Yes, yes, sure.
yeah, so 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 the gerrymandering problem has a set of voters, and the voters, we want to distribute, or we want to partition the voters into some districts. So the gerrymandering on paths means that the voters are on the voters are the vertices of a path graph. So the voters are vertices of a graph. So gerrymandering on path means that the graph is a path graph. So here you have these voters 1 to 11, and they are they're sorry, not 11, 12. This is, yeah, sorry. So 1 to 12, and you have they're the vertices of a path graph. Okay, and so what do we want to do here? We want to divide this into this graph into districts. So is this correct districting of the graph. So note that this, what do I mean here? So here 1 to 5 is in one district, 6 7 is in another district, 10 alone forms a district, but we want a partition of the graph, right? So these vertices, they must also go into some district, right? So every voter has to be in part of some district. So so now, is this a correct districting? No, because we said that we have each district must be connected, right? Excuse me. So correct districting here could be this, right? Like not a correct, like I mean a feasible districting here could be this. So if you look at a district, it since our given graph is a path, if we just know the first and the last vertex uh, of each of the district, then this uniquely identifies the districts, right? So so based on this observation, we will create an auxiliary graph H. So just once the information about what the problem is clarified, then I will proceed with the remaining. Hello. Okay, I will proceed. So so based on this observation that each if the given graph is a path, then each of the district can be identified by the first and the last vertex. Here by first and last I mean this in this ordering, right? So we create an auxiliary graph H, and what we do is that for every pair, so the this should be the basic idea, right? That for every pair of vertices, I can form a district, right? So that means if I say that I have a district 1 6, that means that district is starting at 1 ending at 6. Or I have a district, say 8 10, as it is as here, that means it's starting at 8 and ending at 10, right? So for every pair of vertex gives me can give me a district. So to enumerate, we can get like all possible options of district by if we make a vertex in the graph H corresponding to every pair of vertex in the graph in this path, right? So, and this pair may not be unique, because as I showed in the last example, that one vertex alone can be one district. Okay, so I'll just show you the construction of the graph, but before that, so to proceed with the algorithm, we'll construct this graph, but before that, we guess the number of district that will be owned by P into if it is a yes instance. So let that be K star, which is some number between 1 to, not 1, obviously K is yeah, some number between 2 to K. And so this K star is the number of district 1 by P. We have guessed this, and now we are this is how we create the auxiliary graph. So for this vertex here, V11 means that this is a district. So each of these blue vertices are denoting a district, and this subscript here means that this district starts with vertex 1, ends at vertex 1, and this here means that this starts with 1 and ends at vertex n. So here we create all the district that starts with vertex 1 and ends somewhere else. Here we create all the district that's vertices for the districts that start with vertex 2 and so on. Right now, what we do is that if a district is starting at some vertex, if a district is ending at some vertex I, the next district, there must be a district that is starting from the vertex I plus 1, because at the end of the day I want a partition of the of my whole vertex set, right? So so to encode this, we draw an arc from, sorry, this arc should not be there, from V1 n to V22. So we draw an arc from the vertices, which denotes a district Vij, to a vertex which denotes a district Vj plus 1 to something. Okay, so all the vertices which denotes a district that ends at 1 should have an arc to all the vertices which are denoting the district which starting at 2. Okay, so this arcs shouldn't be there because they are ending at n, so they shouldn't be going to anywhere else. Sorry about that. So now
Sorry, just a quick question. So these are ordered pairs, right? The indices. I think I just, in the sense that you don't have V21, I guess.
no, I don't have V21.
Right. Okay.
Yeah.
Cool. Thanks.
Yeah, Ij are subsets of n.
Yeah, makes sense. Thanks.
Okay, sorry. So yeah. So now these are the so now this set of vertices are now denoting all this possible district, and yeah, we are not repeating anything. So every district is basically represented once here, and now we add this two extra vertices S and T, and S is connected to all the vertices which are starting with 1, like which are denoting the district which are starting from 1, and T is connect, and so from S to these vertices I have an arc, and T is connected from all those vertices which are denoting district ending at N. So again, sorry about these two arcs. Yeah, so now in this graph, and we also have labels on the arcs. So what does this labels means? So then remember that I have guessed that my candidate P wins in K star many districts. Okay, so now every arc here, uh, every district here has some winner, right? So on this arc, I want to label these arcs with the winner of this district. Okay, so if arc is so let's show here. So this the arc which are going out of the vertex V2n must be labeled with the winner of the district V2n. So a arc which is going out of V1n must be labeled with the winner of the district V1n, and so on. So, but if the winner of the district is my preferred candidate, then I keep the arc unlabeled. Okay, and also there is not only just one arc. So I have, for simplicity, I have kept the figure there is only one arc. So we label this, there are multiple arcs, so there are k star minus 1 arcs. Okay, and we label these arcs with the candidate. So here win to n means that the candidate that wins into the in the district 2n. Okay, and as you remember that we have tie-breaking rule unique winners, so we can uniquely identify this candidate. So this means so now we have so just to make the picture more clear, I have drawn the multiple arcs here, but we have here k star minus 1 arcs. Sorry, this should be k star minus 1, not k star. So we have k star minus 1 arcs, and each of these arcs are labeled not only with the winner candidate of this district, but with an integer and the candidate. So yeah, so this is how we draw this. This completes the construction of the auxiliary graph. Now what we have achieved. So now look at this thing, that if I can find S to T path into this auxiliary graph on k plus 2 vertices, what do I get? So forget the S and T, the two extra vertices. Each of the k on this path are corresponding to some district, right, in the graph G. And since we have drawn this arc in this fashion, I have an arc from Vij to Vj plus 1 R for, so whenever a district is ending at J, the next, if on this path you are going to a next vertex, that vertex must correspond to a district which is starting at the very next vertex in your graph G, right? So then each of this, so if I have a S to T path, if you think for a minute, you'd see that the union of this vertices on this path, the district corresponding to the vertices on this path will give you the whole vertex set of G. This basically gives you a K partition of the vertex set of G. Okay, so our first criteria is now satisfied if I can find the S to T path on k plus 2 vertices into this auxiliary graph. And what was the second thing? That I want P, my favorite candidate, my preferred candidate, to win more than any other candidate, right? So here, the all the candidate who are not equals P, for them I have this labels, right? And I have this labeled arcs. And if P wins, I have unlabeled arcs. So what do I want then? I want that on path S to T, I must have K star many district where P wins, right? So K star many unlabeled arcs. And the arcs out of S are unlabeled. So that's why must have K star plus 1 unlabeled arcs. And all the other arcs are labeled, but the labels must be distinct. Why do I want this label to be distinct, and what is the purpose of this multiple arcs here with different labels? So the purpose of this is that since I know that since I have guessed that P is going to win in K star mini districts, so no other candidate or every other candidate can win in at most K star minus 1 mini districts. So if I have distinct labels on this path, S to T paths, right? That means no other candidate, no candidate other than P can win in K star more than K star minus 1 mini district, right? Because there are K star minus 1 mini distinct labels for this candidate. So that for every candidate I have this kind of labels, right? Candidate, comma, and integer, and this integer goes from 1 to K star minus 1. So so okay, so now if after I have constructed this auxiliary graph, this is my goal, that I want to find this S to T path such that I have K star plus 1 unlabeled arc, and the path is on K plus 2 vertices, and there are all the other labels are distinct. Okay. So so I guess most of you are familiar with the K-path algorithm. So this is we will do almost similar, but we have to keep track of the labels, right? Because we want to make sure that the labels are distinct, and there are K star plus 1 unlabeled arcs. So this will be a similar algorithm, but where we are doing bookkeeping for the labels. So as we do for the K-path algorithm, that we define this family. Uh, uh, so here I mean that if IRV means that I have a path on I plus 1 vertices with R plus 1 unlabeled arcs, and I have a path from S to V. So I have a path P from S to V with I plus 1 vertices, and this property means I should have written the property here, but this means that I have R plus 1 unlabeled arcs. Okay, what does that mean? That one unlabeled arc is going out of S, so on this S2V path, P is actually winning R districts. Okay, and now we want to keep track of the labels, so we define this family, which is Q IRV corresponding to the family FIRV. So this is basically where I'm storing all the labels of this path. Okay, and so this formula gives you recursively how to compute this labels and the path for the path. So yeah, this is I guess if you haven't seen this before, this looks a bit scary, but I'll just explain it. So if you have a S2V path, right, then this path, yes, is there a question? Okay, so if there is a S2V path, then this must come to V via some in neighbor of V, right? So we look at all the in neighbors of V, let's say W. Okay, W is a neighbor of V, and now two things can happen. Either P wins at this vertex W, that is the district corresponding to the vertex W, or P does not win in this district. Okay, so if P wins, so then P to W is an unlabeled arc. So then in the remaining path, in the prefix of this path, this S to W path, that is, we are looking for R minus 1 unlabeled arcs, right? So we are looking for a I minus 1 size a path on I minus 1 vertices with R minus 1 unlabeled arcs. So that is why we look at this family. Otherwise, P wins into in this district W. So then I have a labeled arc from W to V, right, with some label J, some candidate win of W and some integer J, right? So we add this to the family, and but what should I have? I should have R unlabeled arc as well, right? So from the family, which is from the path which is on I minus 1 vertices, that is from the S to W path, which is on I minus 1 vertices, there I must have R unlabeled arcs. Okay, so this is how we can compute this family recursively. And but then there could be a large number of labels, right? This family size could be very large. So this is why representative family is used for k paths. And I'll not define it formally, but I'll just tell what we mean to do here with the help of representative family. So look at this example again. So you have this vertices, and this part is say you are yet to explore. So this is the S2V part. Say 1 to 7 is the part that we are looking at now, and we are looking at the district that can be formed here. Okay, and so now say this green is the district where our preferred candidate P wins, and gray is another candidate. So here we have divided this 1 to 7 part into two districts, and where one in one district our preferred candidate wins in this one, and in the other the gray candidate wins. Okay, so there could be another possible districting, this one, where again we have two districts, and one where our preferred candidate wins and the other where the gray candidate wins. Okay, so these two paths, if you look at the property of the family that we defined, what are the things we are storing there? That how many how many the path on how many vertices, right? So the vertices in the graph H corresponds to the districts. So basically the number of districts, the number of times P has won, the number of and the labels. We are keeping track of the labels so that we can make sure that the other candidate does not win more k star more than k star many, k star minus 1 many times, right? So here, if you from that perspective, these two paths these two districting are equivalent, right? Because our candidate green wins once and the gray wins once, and we form two districts, right? So, and we are exhausting from like taking the vertices from 1 to 7, partitioning the vertices from 1 to 7. So what representative family does is that if you have such equivalent prefixes of the path, then we can, instead of storing all possible labels for all possible paths, we will be storing labels for a subset of paths. Okay, so if I have two equivalent prefixes as this two, then I'll be storing say label for just one. And this is good enough, right? Because whatever is happening in future, that doesn't matter, because here in both the cases I'm doing the same. Right. So this is just the rewriting of the same formula that same recursive formula that we use, but instead, so we don't want to compute that because that will give me a lot of levels. So this is what we'll do. Uh, uh, I'm just being a bit informal here, but I'm not telling you what representative family I'm computing, but I will compute I'll keep a subset of the labels. Basically, instead of keeping the whole family of labels, I will keep a subset of that. Okay, so this is and if we do that and then doing this whole computation, this takes the promised an amount of time if we do the calculations so properly. So this gives you a deterministic algorithm. So finally, what you will want, finally we will want that this in place of I want how much k plus 2, right? Where k, because I have to have k districts, so I want that q prime of k plus 2, k star plus 1, and t, because I'm looking for an s to t path. So this, if this family is non-empty and have unique labels, right? Distinct labels, not unique, sorry, distinct labels, then I have a yes instance, otherwise it's a no. So this is the deterministic algorithm for deciding WGM on paths. And now I will move to the randomized algorithm. Okay, so again we are looking at the same family because same we want to do the same thing. We want to identify that the labels that we are keeping are distinct, right? Because this is what we kept in mind when we constructed the graph H, right? So instead of keeping the labels as a set family, here what we want to do is that we will keep the labels as monomials. Okay, so what do we do in same we again have this candidate comma integer as the labels, and this corresponding to this label, every label I want a variable and if the variable appears twice, your monomial will have your monomial will not be linear, right? So at the end, if I want that for every label I have these variables, and at the end I want to compute a polynomial where my monomial will be linear, that is multilinear, linear in each of the variables, which means that none of the labels are appearing more than once. So again, we have only labels for the candidates which are not my preferred candidate, and for the preferred candidate I do not have a label. So for that I add a 1 to the monomial, I multiply a 1. So this will be I don't know if it will be clear or more confusing. So it's just the same computation that we are doing um, for the deterministic algorithm. So what we do here is that we want to store these labels, the monomials corresponding to the labels, right? So if you have path P, this L hat P is the monomial corresponding to the labels on this path, and this is what we want to store. So we can do this again. We can compute this recursively. So the same, if we if I look at a in neighbor of the vertex v, right, then so in neighbor of the vertex v in the path p, okay, then this on in this vertex w, either my preferred candidate p, sorry, there are two p, so the capital P is path, the small p is my preferred candidate p. So the p does either wins or it doesn't win. If it does not win, then I am adding this all possible labels, right, that could be there, because if you remember, H had multiple arcs with different levels, yes, right. So the labels goes from 1 to k star minus 1. So I add these labels, right, and this product will give me all possible way, ways to take a path from V to W, because V to W has multiple arcs, so there could be one of the labeled arcs that I'm taking to go from V to W, or uh, P wins in the district W, then you do not add any label, you just multiply 1, right? And so the labels that were the polynomial remains the same, which it was, but the R increases by 1, obviously, and I increases by 1. Sorry. So now this is how we construct this polynomial, and there is results by Williams in IPL 2009. So I think it is not on my next slide. Yes, it got something wrong happened there. So yeah, I'll just state the result. So it says that if you're given a multilinear, given a polynomial, if the fanning of the in the plus gate is can be unbounded, and the fanning of the times the product gate is 2, then in this so now if you have a circuit to compute the polynomial, then 2 power degree of the polynomial multiplied by the size of this circuit is the time you will spend, and in this time you can decide, there exists a randomized algorithm that can decide and say yes with high probability, that is at least 2/3 probability, or if it is a no, then it will always output no. Okay, so it's a one-sided error. If it is a yes with high probability, it says yes, there exists a multilinear monomial in this polynomial, or if it is no, it always says no. Okay, so so the what was the condition, that my plus gate can have fan in unbounded fan in, and but the product gate must have fan in too. So we can see from this recursive formula that we can build build a arithmetic circuit. So I should also probably say what is an arithmetic circuit. Okay, so I'm sorry, this is where my slides end, so I will move to I'll just write somewhere so that I can explain. Uh, okay, I'll share the screen from my iPad so that I can write. Is it visible?
Yeah, it just says, yeah, we can see the, yeah, now the notes are visible.
Okay.
Okay.
Yeah. So the formula that was there, right? Sorry for that. So the formula that was there was this, right? W in neighbor of V. You know, V is not equals P. Then I look at the polynomial, which is for I. This one W. J, or this is equals to P. Then I look at this. Right. So now we want to compute this to apply the result by Williams, right? We have to show that. Are you getting an echo of my voice?
Yes, there is some echo.
Is it fine now? Can you confirm if you can hear me and the echo is?
Yeah.
Yeah, there's no echo now. Yeah, thanks.
Thank you. Yeah. So now we to use the result by Williams that I said. So what did the result say? That the plus gate. So I want the arithmetic circuit. So the says that the addition gate has unbounded fan-in. And the product gate has fan-in too. Okay. So now, as you can see, so what is an arithmetic circuit? Arithmetic circuit is where you have this gates a plus and product, and it's a acyclic. You can think of it's a DAG. It's a directed acyclic graph. So where at the leaves you are allowed to input any variable. Okay, so at the leaves you can input a variable or a constant, and this. So you get this, and then here you have a gate which could be a plus or a product gate. So suppose you have some input here, and this is another gate. Say this is a product gate, and so finally you keep on doing this. So at the leaf you only give the inputs, and then at the gate you compute either plus or product, and finally you have an output. Okay, so I'm not exactly defining it, but I'm just telling it whatever is required to understand that we can construct a circuit for this uh, definition, from this definition, which satisfy this criterion. So here what we have is this, that this sum is for this sum you have j goes from 1 to k star minus 1 here, right? So for this you can have you will have unbounded fan-in, but the product is always happening between these two. So we have only fan-in 2 for the product gate. So this so you can construct arithmetic circuit for this polynomial using this computation, which satisfy these two criteria, right? So using William result in IPL 2009. Okay, this tells me that there exists a randomized algorithm that will say yes, if that will say yes with probability at least 2/3. That will say yes if there exists a so what are we looking for? We're looking for a multilinear monomial, right? So to find a multilinear monomial, there exists an algorithm, or I can say that will say yes if there exists a multilinear. Okay, probability this, and this is a one-sided error. So or if it is no, or always output no. If no, if that does not exist, multilinear. Okay, so this is and the running time of this algorithm depends on this size of this arithmetic circuit, which is polynomial in m and n. So finally the total time we spend is 2 power how much 2 power the degree of this, right? So the total number of labels is k minus k star, right? Because the k star are the unlabeled arcs, which are for p. So k minus k star and some n power n plus m polynomial in n plus n. So in this much time we can execute this. Okay, so I suppose I am out of time, so I'll not be discussing the 2 power n exact exponential algorithm. Yes, I'll end here. Thank you.
All right. Thank you for the talk, Sanjukta. And I guess we can take 2 minutes for questions if there are any. So if you have any questions, you can just unmute yourselves and ask, or if you wish, you can type in the chat.
Just a quick high-level question. Maybe it was already addressed, so sorry if I missed it. But typically, these districts, you impose connectivity requirements, right? So you want every district to induce a connected sort of subgraph. But I'm just imagining that the connected pieces could sort of look weird because these districts are typically coming from some sort of a map-like structure, right? So I think there are situations where these districts end up looking weird. So are there any studies where they also account for maybe something else like a diameter kind of constraint to say that the districts cannot be like, you know, a long and thin strip, for instance, just to avoid weird looking shapes?
I'm not sure, but there are some studies which are for detecting manipulation in like detecting gerrymandering. So they might have studied this kind of if they're I'm not exactly aware of what they do to detect the gerrymandering. So there might be such studies there that if there are restrictions on how the districts are looking like, but from computational aspect, I would say that this problem is even hard when your graph itself has very small diameter. So
Right, right.
the districts will not have a large diameter because the graph itself has very small diameter. And then also the prediction is hard. So if you were thinking from the
That's true. Right, right. Except is diameter wouldn't be hereditary, would it? I mean, even if the overall graph has small diameter, so for instance, if it's something like a star, but I give you a subgraph which is just a collection of leaves, then it's not even. So I'm not sure if okay. So I agree that. What you're pointing out is that you're very likely to encounter hardness anyway if you pile on an extra diameter constraint. But yeah, I just don't know if the reason for that is that it's already hard on graphs that themselves have small diameter. Although maybe okay, so maybe you're right about that as well. So sorry, I just need to yeah, I just need to parse that a bit carefully. But yeah, thanks. That's very helpful. Thanks a lot.
Yeah, I guess I got your question right? You were asking that are there some studies where there are some restriction on how the district can look, right?
Right. And it seems like diameter is a natural way to quantify it. Maybe there are other ways of quantifying it as well in terms of spread or, yeah, basically. And yeah, it also makes sense that if you're trying to detect this kind of manipulation, then awkward looking districts would be the first thing that should raise suspicion. So it would be interesting to see if that can be quantified in some way. And
Yeah.
off the top of my head, I thought that diameter would be a natural way to capture it. But yeah, so I think so your point is that so you had the complete graph example and the K2n and so on. So these are all graphs that
The
already have
probabilities
small,
hard
yeah.
on when the diameter is 4. So there are some more hardness result that I didn't talk
I
about.
see. I see. Okay.
And there
Sure.
is also another recent hardness result for trees where the diameter is bounded, like 3, 4, something like this.
I see. Okay. Yeah. All right. So I think those probably already have implications. Makes sense. Okay. All right. Thanks again. Yeah.
May I also ask a question?
Yeah, sure.
Do you think first of all, thank you for that talk. My question is, so you presented an algorithm for path or 2 algorithms. Do you think it works? These algorithms also work for disjoint union of paths. So the graph where all the connected components are paths. Do you think the algorithm also works in that case? Because when we look at this program, we found that when the graph is disconnected, the program seems to be a bit more difficult than when it's connected. Say when you have isolated vertices, it seems that you can create harder instances based on isolated vertices. So do you think your algorithms also work for disjoint union of paths?
No. So I cannot recall if we actually looked at the scenario where we have disjoint union of parts, but this is very I think we did. And if you have, let's say, like many connected components, then it's obviously this I don't think this will work. You need something extra.
Okay, thank you.
So I didn't present the algorithm for general graphs. Obviously, that one does work for if you have, yeah, I think that one works if you have disconnected like the graph G is not connected. The algorithm that we have on general.
It will be strange if it doesn't work out, right? I'm not entirely sure, but yeah, but anyways, thank you for answering the question.
Yeah, thank you for asking.
Okay, maybe one last quick question, if there is one. Okay, I suppose not. All right then, thank you once again for the great talk. It was really nice to have you, Sanjukta. And thanks to the audience for being around. So we conclude our session for today here now, and see you all next week. Thank you. Bye.
Thank you. Bye bye.